Alright, I'd now like to talk about alcohol additions to epoxides. And there's two we'll be dealing with. An acid catalyzed one is going to give this product where the OCH3 ends up being placed on the more substituted carbon. And this one where the OCH3 ends up on the least substituted carbon. And both of these are a consequence of two different mechanisms. The first one is going via an Sn1 mechanism, and the second one is going via an Sn2 mechanism. Now let's talk about this in context of the kind of question you're going to see on the test. What you're going to see is an epoxide that is asymmetric. It's going to be more substituted on one side than the other. Now when I say the words more substituted, what I'm talking about are the number of carbons connected to each carbon on the epoxide ring. In this instance, we have one carbon connected to this carbon on this side, and we have no carbons connected to the carbon on this side of the epoxide. Thus this is more substituted and this one is less substituted. In this kind of problem you're actually given the products, so you know where the OCH3, where this alcohol group has ended up attaching. In the case of the acid catalyzed one, that's the one with the H+, the OCH3 has ended up on the more substituted carbon. In the base catalyzed one, that's the one with the CH3O-, the OCH3 has ended up on the least substituted carbon on the epoxide. Alright, let's look at the top one first, that's the acid catalyzed one. The first step in the mechanism, and we've seen this happen before with our ethers, is the O takes the H+, and we end up getting this structure here with a positive charge on the oxygen. Now we know which side the OCH3 has ended up on, and it's ended up on the more substituted carbon. Since it's a more substituted carbon, what's going to happen is it's going to react via an Sn1 type mechanism. So what's going to happen is this is going to break first, leaving a positive charge on this carbon atom. And then the CH3OH is going to come in and attack that positive charge. So this is going to be a two-step process. Then in the last step we'll lose the H+, and we'll end up with our product. So the OCH3 ends up on the more substituted of the two carbon atoms. Just reminding you about what the Sn1 mechanism looks like. In the Sn1 mechanism, when we start off with a substituted carbon, we end up with a positive charge, and then some kind of nucleophile comes in and attacks that positive charge, and we get our product. So it's a two-step process, and the reason it's a two-step process is because we can't get the Cn- to come in and attack that and kick that out in one step, because there's just too much stuff going on around this carbon atom. There's not enough room for the Cn- to actually get in. And the other reason the Sn1 is favoured is because the substituted nature of this carbon, the more carbons there are around this carbon, the more stable this cation is going to be. So for the same reason, we don't get this situation occurring with this compound. We don't get the CH3OH coming in and kicking this out in one step. That would be an Sn2 type process, and that's just not what's going to occur. In Sn1 processes, the first step is always the breaking of a bond to form a carbocation, and then in the second step the nucleophile comes in to attack the C+. And that's exactly what's happened here. Let's go take a look at the other one now. Now in this case we can see the OCH3 has ended up on the least substituted side, which happens to be primary. So this is going to be a prime candidate for an Sn2 type mechanism. Now given the choice of these two reagents, I'm going to react the charged one, because that's always the more reactive of the two. And since we know it's attacked on this carbon here because of where it is in the structure, we're going to choose to do so by an Sn2 type process. If you'll remember what an Sn2 is, an Sn2 reaction is a concerted process where we have two arrows in the diagram at the same time, where we're forming this bond and breaking this one simultaneously. Okay, now the negative charge on that oxygen can remove a proton off the methanol. That's the solvent here. And we get our alcohol product. Right, let me show you what's happening here. We've got two electrons on the oxygen that are going to form a bond with this H, and simultaneously the bond between this H and this OCH3 is going to break. So what's going to happen is this is going to become negative OCH3 or CH3O-, and that's what makes this catalytic, because now we've used CH3O- and we've formed it back again at the very end. Just to remind you what an Sn2 reaction looks like, here's a typical Sn2 process. Cn- comes in, attacks the C, and kicks out the Br all at the same time. And that's an Sn2 process. Now remember that the reason this could not ring open first is that it would form, well, it forms lots of nasty things, but it would form this kind of thing where you've got a primary carbocation which is very unstable. So what I'm talking about would be this kind of thing, and that just doesn't happen. It has to be a simultaneous thing where the CH3O- comes in and this opens at exactly the same time. So we're not going to see anything like that occurring. So hopefully that explains to you why these go via different mechanisms, and hopefully I've explained to you the mechanisms in good enough detail.